Hello, welcome to my talk on boundary element method for wave energy conversion, part 4, on forces, motions, and wave energy conversion. This talk focuses on how the hydrostatic and hydrodynamic forces and the moment can be calculated once the relevant potential function have been solved. This includes the hydrostatic forces, wave exciting forces, as well as the radiation forces in terms of added mass and the radiation damping coefficient, and on how the dynamic equation is established and solved in frequency domain. With the implementation of the power takeoff system into the dynamic equation, the dynamic system could extract energy from wave, with the large net energy, the averaged positive energy being our target. Once the potentials of the diffracted wave and the radiated waves are solved, together with the known potential of the incoming wave, we can calculate the fluid pressure based on the Bernoulli's equation, given as this. Here, capital phi is the time-dependent total velocity potential, and the phi here is the complex amplitude of the potential. Here, the time factor is now expressed as the exponent of I omega t instead of the minus I omega t I used before. This is following the reference given by Wahr's manual. It should be noted both exponents of I omega t and minus I omega t can be used, and the result should be same if the interpolations can be made correctly. So use the same exponent for the time factor as that in Wahr. This will lead to the same equations as we have seen in Wahr's manual. For wave and structure interaction, the higher order pressure is given by this. In the wave structure interaction, the fluid velocity is normally quite small. Therefore, the second order fluid pressure is normally an order smaller than the first order dynamic pressure. Therefore, the second order fluid pressure can be omitted in the wave structure interaction problem. As such, the pressure can be linearized and given as this. This is very good for the analysis of the first order forces and motions for the floating structure, although the second order force would be important for the mooring system. So in frequency domain, the pressure can be given in this form from this expression. And if we employ the potential decomposition given in this form as we talked before, so we can obtain the pressure expression given as this. Here we can see the summation on J from 1 to 6, meaning the 6 degrees of freedom motion. J equals 1, 2, 3 are the translational motion, surge, sway, and heave, and J equals to 4 to 6 are the rotational motion for roll, pitch, and yaw. As we have shown, the forces of the fluid acting on the structure is given as this for the 6 components of the force. Here, Ni is the extended normal vector component, with the first three components being same as the conventional vector n, and the last three components are defined as the vector r cross-timing the vector n. Vector r is the vector from the origin of the coordinate to the small surface ds here. So substitute the fluid pressure into the integral for the force component. We have the force Fi given at this. Here we should notice the difference of the subscript I, the Fi and the Ni here, and the imaginary unit I here and here, the letter I. Further separate the total forces. We can have the expression for the hydrodynamic and the hydrostatic forces as this. The first term in the expression is the wave excitation, and the second term is the radiation force, and the last term is the static force. For formulating the hydrodynamic and hydrostatic forces for the structure motion, here the parameters for the hydrostatic are given for reference. The first parameter is the volume of the fluid displaced by the structure. Lambda is given as this. This expression means the volume of the fluid displaced by the structure can be calculated in three different ways, in three directions: on x-axis, on y-axis, and on z-axis respectively. And all three volumes should be same if the calculation is accurate enough. Such information can be very useful in wave structure interaction analysis, when we need to check whether all the generated panels are oriented correctly. If all panels are oriented correctly, these three volumes should be very close if they are not identical. The other important parameters are the coordinates of the buoyancy center, xb, yb, and zb, which are given in these formulas. The coordinates of the buoyancy center are needed when we calculate the hydrostatic restoring coefficient for the structure. We will see this later. In this slide, the hydrostatic forces are calculated. The formulation of the hydrostatic force is calculated by this formula for 6 components. Here I equals to 1 to 6. Principally, these hydrostatic forces are so-called zero-order forces. If we calculate the hydrostatic forces directly, use this formula. These zero-order forces would be the largest for wave structure interaction, but they would be balanced with the structure weight in its equilibrium. For instance, in equilibrium position, the buoyancy would balance the structure weight for the freely floating structure. However, in the analysis of the wave structure interaction, due to the motion of the structure, there will be the net hydrostatic forces given at this, which are caused due to the structure motion, Cj. It is the deviation of the structure away from its equilibrium position. The net hydrostatic forces can be regarded as the restoring forces, which are the first-order hydrostatic forces proportional to the structure motion Cj. Following the reference, the non-zero coefficient Cij are defined as this. Here we can see total 8 out of possible 36 are non-zero, and the other coefficients are all zero. In addition, depend on the symmetry of the floating structure, some of these coefficients might vanish. For instance, for a vertically floating circular cylinder, C34, C35, C45, C46, and C56 would be all zero. Based on the potentials for radiation waves, the corresponding pressure would be given as this in frequency domain. So, if we substitute the pressure into the surface integral for the radiation force, we have the expression as this. And we exchange the order of the integral and the summation, we have the expression as this. Now we can define a complex coefficient Fij, which can be understood as the complex force in the direction or motion mode I due to the motion of unit velocity in the direction j. And if we separate it into the real and imaginary part, given as the expression as this, we can have the added mass, Aij, as the real part of the complex coefficient Fij, and the radiation damping coefficient, Bij, as this. Use the expression Fij, we can have the radiation force as this. This is the expression in the frequency domain. If we write the expression back into the time domain, we should have the expression as this. So here we can clearly see that the added mass Aij is related to the acceleration, and the damping coefficient Bij to the structure velocity. Based on the definition, the wave excitation on the floating structure is corresponding to the fluid pressure due to the incoming and the diffracted wave given as this. Therefore, the wave excitation would consist of two parts. The part due to the incoming wave, which is also called the fluid clear-off force on the fixed structure, and the part due to the diffracted wave by the structure. So this expression is the direct integral for the wave excitation if the diffraction potential phi7 is solved. Here, the incoming wave potential phi0 is a non-function if the wave amplitude and frequency are given. Since the wave excitation is defined as the wave excitation force acting on the supposed stationary structure, while the structure motion has been considered in the radiation problem, thanks to the superposition principle. Thus, this wave excitation would be independent of the structure motion. For the rigid body motion in waves, the dynamic equation can be given in a similar form as that in the Newton's second law of motion. The left-hand side is the mass and the acceleration, and the right-hand side is the force acting on the floating structure. But should be noted, the motion would be in 6 degrees of freedom motion. The forces acting on the structure include the wave excitation, the wave radiation, and the restoring forces. Here, mass is given in a form of matrix, capital Mij given in this matrix. Here, m is the mass of the structure, and xg, yg, and zg are the center of the gravity of the structure, and capital I11, I22, and I33 are the moments of the inertia, and other I12, I21, I13, I31, I23, and I32 are the products of the inertia. It should be noted here, all the moments of the inertia are with regard to the principal axis, that is, with regard to the center of gravity of the floating structure, regardless whether the reference point, the origin of the coordinates in the plot, is same or not with the center of gravity. In reality, the dynamic equation must be given in time domain, as shown here, as the equation for the rigid body, the dynamic equation for the rigid body. However, for the 4 linear dynamic problem, frequency domain analysis would be simple and much faster. In frequency domain, if we have a complex amplitude Cj, the motion can be expressed as xj equals Cj times the exponent of I omega t. And for this, in frequency domain, we can obtain the velocity Vj as I omega Cj, and the acceleration Aij equaling to minus omega squared Cj. As we already shown before, the radiation force, the static force, and the excitation force are all given in the frequency domain. So if we put all these forces and the motions together, we could have the hydrodynamic equation for the 6 degrees freedom motion for the structure, given as this, in a form of spring, mass, and dashboard. So here we can see capital Mij plus Aij is the total mass matrix, and the Bij is the radiation damping coefficient, and the Cij is the restoring force. Fexi is the excitation force. The frequency domain dynamic equation can be simply written as this compact form. Here, capital Cij is defined as this. For this frequency domain equation, the relevant parameters, the excitation force Fexi, the added mass Aij, and the radiation damping Bij, can be all calculated from the boundary element method as we introduced in the previous talks on this topic. Here, some famous boundary element methods are listed. This includes WAMIT, Wave Analysis MIT. This is the most popular and the most used commercial code for both research and development. ANSYS Aqua is another commercial code with the very good integrated graphic interface as a part of the ANSYS code. NEMO is an open source which can be downloaded from this website. In many ways, NEMO is very similar to WAMIT, but not so powerful as WAMIT. In addition, there are many in-house BEM codes developed in the different organizations, such as in many universities. And the other parameters, capital MIJ and CIJ, can be calculated if the structure is given. So from the frequency domain dynamic equation given as this, we can easily calculate the motion amplitude mathematically given in this formulation. Here, Cj is the complex motion amplitude. As a convention, the response amplitude operator is normally given as this Zj equaling to Cj divided by A, the wave amplitude. As we can understand, the response amplitude operator Zij is a complex response, a long-dimensional expression which would depend on the wave frequency omega and the wave incident angle beta. For a wave energy converter, the next step would connect a power takeoff system to the dynamic system of the floating structure for extracting wave energy. Here, we take a simplest example, the bottom fixed point absorb, which utilizes the heave motion of the floats for wave energy conversion. In fact, such a principle can be seen in practical developments such as core power and sea-based device. For genetic application, the linear PTO can be given in this formula following the reference. Here, MPTO and CPTO are often used to change the characteristics of the dynamic system. For instance, in the control system for improving wave energy conversion. And the BPTO is the coefficient of the PTO damper. The negative signs in the expression means the PTO force would resist the motion. In the time domain, the motion x3, the velocity x3 dot, and the acceleration x3 double dot are given as this. And we can see here the velocity has a phase difference of 90 degrees with the motion ci here, and the acceleration has a phase difference 180 degrees, indicated by the negative sign here. So if we drop the time factor, the exponent, we can have the frequency domain expression for the motion, velocity, and acceleration. Therefore, in frequency domain, the power takeoff force would be given as this. So put the power takeoff force into the dynamic system of the floating structure. So we have the dynamic equation in frequency domain as this. And the amplitude of the heave motion can be easily solved given as this expression. And after that, the average power conversion P bar can be calculated given by the general formulation as this. Here V3 star is the conjugate of the velocity V3. If we take V3 as this, its conjugate would be given in this form. Here in this slide, the talk is on the average power based on the power takeoff force. As we have seen, the PTO force can be proportional to the motion with C PTO, or proportional to the velocity with B PTO, or proportional to the acceleration with M PTO. So here we will see the corresponding average power for the individual PTO force for these three terms. As we have shown this before, V3 would be given as this in frequency domain, and its conjugate is given as this. If we time the velocity and its conjugate, we will have the expression as this and here. So regardless what are the velocity expression, the products of these two parameters would give a real number as this. If we take the example as a generic complex number A plus IB and time its conjugate as this, so we have this times this, and we have A squared plus B squared. So this is actually the module of this complex number squared. In the derivation, we will use this expression. So for the first part, P1 with the MPTO, so the force given by this and the velocity conjugate. If we substitute the velocity conjugate, we have this. And take all this real number out of the real number operator RE, we have the expression as this. And we can see here, so inside of the real operator RE, it's a pure imaginary number. Therefore, the operation would give the average value 0. And the average power for the second term of the power takeoff force, we have the expression as this, and the substitute of the velocity conjugate, we have this. And if we take the real number omega and B PTO out of the RE operator, we have the expression as this. And we can see inside of the RE, we have a pure real number. Therefore, the average power would be given as this. For P3, it would be very similar to P1. The details were not given, but it would be 0. What happened here is for P1 and P3, the PTO force would have a phase difference of 90 degrees to the velocity. Therefore, for P1 and P3, the average would be 0. While for the power takeoff force, the second term, the power takeoff force and the velocity would have same phase. Therefore, we can obtain the net average value from this damper PTO. Although the average value for P1 and P3 are 0, this PTO force indeed convert wave energy, but only in half of the wave cycle. And in the other wave cycle, the power takeoff system needed to feed the energy back into the wave. This is why the averaged power for P1 and P3 are 0. In the next 2 slides, a summary will be shown how we can use the BEM codes for studying wave energy conversion. Generally, for practical wave structure interaction problems, the linear solution to the problems are generally very good and reliable. That's why the boundary element method, for instance, Warmit, ANSYS Aqua, and some other BEM software packages have been regarded as the industry standard. This is true for wave energy conversion. For using the boundary element method for wave energy conversion, here the commercial code Warmit is used as an example, but it should be noted other BEM code would be in a similar procedure. Step 1. Panelize the wet surface of the structure into many small panels, as seen in this figure for the circular cylinder. You can specify whether the sources or doublets to be distributed, as seen the dots on the panels. And in most cases, the sources are distributed, while the doublets are only useful for some rare cases, for instance, for the thin structure, for which both sides of the surface are wet. Step 2 is for solving the Laplace equations of the different potentials. More specifically, the boundary integral equations for the diffraction potential and the radiation potentials, as we have talked about in my previous talk on boundary integral equations. For achieving that, you need to specify the wave frequency, the wave incident angle, and the water depth. Step 3 is for calculating the force and moment acting on the structure. Once the potential are solved, the fluid pressure can be calculated using the linearized Bernoulli's equation for the wave excitation and the radiation forces. To do that, you might need to specify the reference point. For instance, the center of gravity or some other specific point, such as a point at the calm water surface. Step 4 is to calculate the responses of the motion in the wave of unit amplitude, with and without the power takeoff system. You may need to specify the mass matrix, center of gravity, and the motion modes. For instance, for the fixed or floating motion mode. And you may need to specify the PTO force coefficient if the linear PTO is added to the modeling. Step 5, to calculate the power conversion, either in frequency domain as shown in the previous slides, or in time domain where the power conversion time history can be seen, and thus the average power can be calculated. This part of the modeling might be carried out using some simple programs. You may also calculate the average power from the responses with the PTO system. In the next talk, I will give some examples to show how to use the boundary element method for wave energy conversion.